Imagine you've got a band here, you cut it and you stretch it out, you have a really skinny rectangle. The length of the rectangle is the 2 pi x. The skinniness there is just this, how is the change in value of x from the inside to the outside. It's something infinitesimally small. So we have a dx there. So this becomes I hat k q big R integral 2 pi x dx. Oh, I lost my sigma. Sigma times that, times sigma. Divided by r cubed. We have a right triangle again. What does r squared equal? I am making the assumption that everyone in here has better eyesight than I've got.
Capital R squared plus x squared.
Yes. And the comment was, I looked at this and I said, wow, read that really small. And I thought, no, wait a second. They're all young. You can see this. I'm assuming your glasses prescription is close enough to up to date.
It works.
Okay. I don't remember if I told this story before. I had a student a couple years ago who sat basically where Devon's sitting now, who did not have his glasses for pretty much until the last, I think, 2 weeks of school. He finally got glasses that worked. But he was constantly saying, what does that say? I can't read it. So if you're having issues with your eyesight, I suggest moving closer. So r cubed is just big R squared plus big X squared, that whole thing to the 3/2. And so that is my denominator, x squared plus big R squared to the 3/2. And pulling out the constants, I get I hat k cubed big R sigma 2 pi integral x dx over x squared plus R squared to the 3/2. We now have a single variable, limits of integration next. What are the limits of integration of x? And
Negative infinity to infinity.
you were ahead of your time before.
0 to infinity.
There we go. X is the distance from the center of my circle. The smallest it is
Yeah.
when the circle is infinitesimally small. Okay. From 0 to infinity. It is really tough being unstuck in time. You just pop back in, you're never quite sure what the question was. Unstuck in time, who knows the reference? Slaughterhouse 5, I believe. It's one of the Vonnegut's, I think it was Slaughterhouse 5. Have any of you read Slaughterhouse 5? There were basically 2 books in high school that were required reading that actually I enjoyed. Slaughterhouse 5 was one of them. Catch-22 was the other. The rest of it, there's a reason I did physics.
Is it Slaughterhouse?
Yes, Slaughterhouse 5. Not necessarily a happy book. Kurt Vonnegut was I believe a POW. He was somewhere near Dresden when they got firebombed during World War II. So there's I think it feels like an undercurrent in a number of his works about some of the horrors that he saw. Anyway, back to happier matters. Calculus. How do you solve this one?
I imagine it's on a sheet somewhere.
It is on a sheet somewhere, but if we didn't have the sheet, how would you do it?
Trig sub.
Colin was ahead of his time last time. Or was it Devon? Devon was ahead of his time last time.
With the use
Oh,
of.
yeah.
Yeah,
You
use
got the
substitution
U
works this time. Because we got x squared, and when we do
Only
du,
two
we get an x.
That x.
Pardon?
I'm just saying now the one over 2x, it'll take care of that x.
Yes, it will.
Okay.
So, but it is on a sheet. It depends on which way you want to go about it. Math or sheet?
Sheet.
Sheet, all right. So 3 halves. Oh! That might actually. I don't have that one on the sheet. I expected you apparently to be able to do the U substitution. Shocking. All right, so let's say you get on the test and you're faced with that and suddenly your mind blanks and you think, I know how to do U substitution, but not at this moment. Just say, what's the generic formula for this? And I'll look it up and write it on the board. So U is equal to x squared plus r squared. I apologize for leading you down the wrong path there, 2x dx. So we end up with the integral, I got a half there, so divide by 2, divide by 2. So I get x over dx is du over 2, which cancels out with that one, so I'm left with an I hat k q r sigma pi. Du over u to the 3 halves. Question for you in Calc 2. When you do U substitution, there's 2 approaches that I take. One, we can change the limits of integration to match what we have for U, or we figure out what this is, we plug x back in, and then use the limits of integration of x.
You should figure out what that is.
The limits with this?
Mm-hmm.
Okay. So if I plug in 0 into this, I get r squared. Let's see, so x, yeah, so when x is 0, u is r squared. And when x is infinite, it's infinite. And this integral right here, again, I prefer the negative exponent version than the fraction. That's just me, eventually. What is the integral of this?
Negative 1/2 u to the negative 1/2. With a negative 1/2 in front.
You divide by it. Because when you take the derivative, the s cancel out. Although what you said, I've seen that, found there was a common mistake in the integrals with negative signs. And so I got I hat k q r sigma pi. With a negative 2 up front, and then u to the negative 1/2 from 0 to, from r squared to infinity. Let's just write it as 1 over square root of u. Negative 2 I have k q r sigma pi. We plug in infinity, we get 0. Minus, plug in r squared, we get 1 over r. So r's cancel out. So I'm left with 2 pi k q sigma I hat. In other words, away from the sheet.
Would the r be squared?
It's square root of u.
Oh, the r, okay, never mind.
if you're looking at some of the videos, I typically don't change the limits of integration. I get to this point and then I plug the value of u back in. I take the extra step. I'm assuming some childhood scar causes me to do that, but just if you're watching the videos and you see that I don't change the limits of integration, it's because I plug that back in and use the original limits of integration. This is the more sophisticated way. All right, I'm going to look at this slightly differently, using the same thing I did before, the fact that Coulomb's constant is equal to 1 over 4 pi epsilon sub naught, assuming a vacuum in space. So I get 2 pi 1 over 4 pi epsilon sub naught, q sigma I hat. Pi's cancel out. I get a 2 in the bottom, so I'm left with q sigma I hat over 2 epsilon sub naught, which is a slightly simpler form. Or at least it looks like it to me. Not dealing with that pesky pi. Let's think about the implications of our answer. If I double the distance for that q is from this infinite sheet, how much does the force change?
It doesn't.
Correct. If we have an infinite sheet here, it doesn't matter the distance from it. It is the same force. Assuming the charge distribution is even. This becomes incredibly important when we start looking at capacitors. The parallel plate capacitor is you've got two large sheets, or two large pieces of metal, really close to each other, so that this distance is minimal, is typically less than 10% of this distance. If that is the case, we can assume that the infinite sheet approximation. The bigger gap that you put in it, the less valid that approximation is. And then as a physicist or an engineer, you'll look up the formula. But for a lot of the capacitors we do. Well, if you think about what a capacitor looks like. This might look fairly big, but you basically have two sheets of metal that are with insulator in between so they don't touch, rolled up. So you'll have these two really huge pieces of sheet in there, which will be, a matter of, well, you'll be pulling out the micrometer to measure the thickness. So it is reasonable to assume that we can have two really large sheets, or two really large conductors with something incredibly thin in between, that the infinite sheet approximation is valid. And for those who are watching this, I just pulled out a capacitor. All right. Any questions? All right. I do want to point out that we just went through derivation for the infinite line of charge, and we went through the derivation for the infinite sheet, and for the spherically symmetric distribution of charge. We will do it again. When we get to Gauss's law, which is chapter 25, we'll find an easier way of doing everything we just did. But we will come back to, and you'll see that we get the same answer to give some validity to Gauss's law of electricity. The actual proof of Gauss's law, I'll do a pseudo derivation of it when we get there, not the full blown derivation. I think there's a video where I did the full blown derivation of Gauss's law. Any other questions before I finish erasing? Hopefully if you have questions, it's not about this stuff.
So like on the test, will we be given almost the same questionnaire? have to solve for it, or is this just proving an equation?
The test will be more practical than, I'm not gonna ask you to derive it. A lot of the reasons I go through derivations is, one, to show some of the math, but also to give justification for the stuff that we're doing. And one place where you actually might need to do it, and I've done this on more than one test, is we did the infinite line of charge. Suppose it's a finite line of charge. And what changes are the limits of integration. So you need to be able to at least get to that point where you can plug in the limits of integration, which for most people is to start from scratch and go through the steps. But deriving this stuff, I typically don't ask you to regurgitate that. That's right. I assume that woohoo was for physics in general, not just any specific thing. And I think one, oh. So let's take a look. I think it's the last topic from chapter 23. The dipole, the electric dipole. An electric dipole is, the simplest view of it is I have two charges, negative Q and Q, that are separated by some distance S. The distance between them is fixed. And you might wonder, how realistic is this? If they are of opposite signs, then shouldn't they be attracted to each other? Think polarized molecule. A water molecule can be simplified down into, we have a positive side and there's a negative side, and they're relatively fixed distance apart. And I have some charge over here. The distance from the middle to this charge, what do I make, L? And again, sticking with notes, do I want to keep that or? This will make it R, since that's what we're using for Coulomb's law. And we have some charge Q here. So the question is, what's the force on Q? The other classic example of this, we have it all in the same line, or I could put Q perpendicular to the line that connects little q and big and negative little q. So this will be the force on big Q from Q plus the force on big Q from negative Q. Because one of them is going to attract it and the other one's going to repel it. The way I have it written up there, is big Q going to be attracted to the dipole or repelled by the dipole?
So that's gonna be like even, I guess.
You said repelled and then you changed to.
No, it says, I guess repel, because it's gonna be like, don't they gotta be like even, I guess? What's on the one Q side versus the other Q side?
Yeah, as in even distance?
Yeah.
Yeah.
Okay.
So it should be repelled, because that's gonna be the dominant one. Not by much, but enough. So let's go through it. Well, I'm gonna stick with K because it's easier to write than 1 over 4 pi epsilon naught. So I got K, little q, big Q, over, well, what's the distance between big Q and Q.
R minus S over two.
Little r. Squared. And so that is going to be repulsive. What do we make that the positive direction to the right? Minus the one that's going to attract it. Okay, little q, big Q over R minus, so R plus S over 2 squared. This is just K Q1, Q2 over R squared. I'm going to factor an R squared out of each of the denominators. So K little q, big Q over R squared, 1 minus S over, so you factor R out, if that's squared, okay. S over 2R squared, minus K little q, big Q, R squared, 1 plus S over 2R squared. Have you dealt with binomial approximations? Okay, I'm gonna guess that's a no. If I look at just, well, let's just do it generically. 1 plus alpha to the nth power. Well, if I just did 1 plus alpha squared, that's 1 plus 2 alpha plus alpha squared. 1 plus alpha cubed, the whole thing cubed. 1 plus 3 alpha squared plus 3 alpha plus alpha squared, alpha cubed, there we go. Binomial expansion, I'm hoping this is familiar to you.